Hello again. In this video, we'll talk about the empirical assignment for Chapter 14. In this assignment, I'm going to have you do a forecasting exercise for inflation, and we'll measure inflation using the Personal Consumptions Expenditures Index. It's the same index the Fed watches when it decides monetary policy. This is probably one of the harder programming assignments you've had so far. In fact, I'm pretty sure it is. So what I'm going to do is do a similar exercise, do all the same things, but I'll use GDP instead of price data. And then you'll need to just take the do file that I post and try to amend it for your program. And hopefully you'll understand what you're doing as you go through that exercise and try to fix the program so it'll work for inflation. Let's see. Let me pull up the program here and we can just get started that way. So the first thing it's going to ask you to do is to determine whether the data has unit roots or not. Because remember from the chapter and from the lecture, if the data has a unit root, if it's non-stationary, then all the statistical tests are going to be biased, the coefficients are going to be biased. So we want to take care of that unit root, usually by differencing. That's what we'll do here to get rid of it. We'll assume there's a stochastic trend in the data and difference it to get rid of the trend. Now, sometimes there's more than one unit root. There can be two unit roots. In your problem, you're going to end up not just differencing the price data. So you'll read in something called PCEP. Then you'll take a difference of that, a log difference of that to create inflation. And that still has a unit root, as you'll find out when you, oops, I gave that away. When you do the exercise, and then you're going to need to difference the data to look at the change in inflation in order to have a stationary series. Once you have the change in inflation, if you want to predict inflation, it's easy. If I know the change at time t, and I know what inflation was at t minus 1, which I'll do, I can predict inflation at t by just adding those together. Take the value at t minus 1 plus the change, and that'll give me the value at t. And so working with the change in inflation doesn't really stop us from making forecasts about inflation itself. We just have to realize we're working with the change. Okay, let me go up here to the top of the program here. As I said, the first thing you're going to do is do a unit root test, a Dickey-Fuller, augmented Dickey-Fuller unit root test. But before we get there, let me just go through the usual stuff at the top here. So nothing new here. There's a delimiter, clear everything, close in the old log files, make sure it pages right, read in the data. Now this is a little bit different than before. I'm actually reading in an Excel file instead of a DTA file, instead of a Stata file. So this is, we've been working with DTA files because they're faster, it's more efficient. When you have huge data sets, it's much better to use a DTA file. So you need to get used to how to do that. But you can also read them in directly from Excel this way. And then we just tell it that the header is in the first row. So this just tells it that the names of variables, this first row, are, the names of the variables are in the first row. Let me make this a little bit bigger. Maybe that'll help. Maybe you can see it a little better then. So this first row command here just tells it where the variable names are. Okay. This just as a reminder of what the data set is you're working with. Yours is a little bit different. Yours will start in, I believe, 1957. This one starts in 1947 and ends in 2016, and it's quarterly. And the variable I'll be reading in is RGDP, real GDP. So this reads in that variable, RGDP. It's the only thing on this data set. And then the first thing we have to do is this command right here. In Stata, or Stata, I'm never quite sure how to say it. In Stata, you have to declare that the series is a time series. So you have to tell it what the date variable is. Unfortunately, in the data set, there isn't a date variable, so you have to create one. This command will always work so long as this is the first observation in your series. If it's quarterly data, this will work. I'll explain what this TQ command does in a second, but if it were monthly data, this would be TM instead of TQ. If it were annual data, it would be TY. You can just look that up in the search for the help. You can just search for TQ and it'll explain all about all the various frequencies that you can use. You can even use weekly. I think that's TW if you wanted, but we'll only have monthly, quarterly, and annual. So what this does is it creates a series of numbers that are associated with the dates. Let me explain a little bit about how Stata handles time series data. So what it does is it has an internal number system where it sets 1960 equal to 0. So 1960 is always 0, period. So that's the reference point. 1960 is 0. So the way Stata numbers time series data, it works with these numbers rather than the date. So it needs to know what these numbers are. So if it's quarterly data, 1960 Q1 would be 0. If it was monthly data, then it would be 1960 M1 would be 0. And then 1960 M2 would be 1. And so on. We have quarterly data, so it works just the same, but for quarters. So 1960 Q2 is 1, Q3 is 2, Q4 is 3, and so on. And then it goes backwards as well. So if you have dates before 1960, they're numbered with negative numbers, just like you'd expect. What that command TQ does in the program, so for what you see here is a TQ, it takes that date and it converts it to a number. So for instance, let's try displaying TQ of 1973 Q2. Let me copy that, hit it here, let's display that. And as you can see, it tells me that's number 53. So 53 is associated with 73 Q2. Those are always going to be associated together. And so this returns the number associated with the date. Now, there's another numbering system that Stata uses, and what it does is it takes the first, and that's this underscore n. It's a system variable. It's accessible. You can use it. When you read the data in, what it does, my first observation, so let me type this in here. So for the underscore n numbering, observation 1, which for me is 1947 Q1, for you it's going to be, I believe, 1957 Q1, will equal 1. And then observation 2, 1947 Q2 is 2, right up to the end of your data set. So there's these two different numbering systems in there. So the underscore n just goes from 1 to t. So observation 1 will be that, and then observation t will just be whatever number is the last number in your data set. Now this command, this first command in the program, all it's doing is giving us the Stata numbers, these numbers up here for the data set. So what it does is it says generate a new variable called datevar. In this TQ 1947 Q1, let's see what that is. Let's display that. That's a minus 52. Okay, let's go back to here. So what this is going to do is it's going to add, this is the very first observation, so this will be a 1 and minus 1. So it's saying the first date var is this minus 52 over here. Now this does it for the whole series. So when this is 2, what it's going to do for the whole series is it's going to take this minus 52 and it's going to add minus n, underscore n minus 1 to it. So for the second entry in the series of the series date var, n will be 2. Underscore n will be 2, minus 1 is 1, so we'll get minus 51, minus 52 plus 1. For the third entry in date var, which is the Q3 entry, this will be 3, so it'll add 2 to this, and we'll get minus 50, and so on. So this date var will give us those numbers. Oops, did something I didn't mean to do there. So that's all there is to that. Let me show you what the date var does. Let me just run this program real quick. Let me take out this format command because I'll explain that in a second. So let me comment that out. Let's do. This is a graph we'll talk about later. Those are actually the forecasts. Okay, so let me just look at the data here and see what the date var. Here's the date var variable we created. See, it's minus 52. That's when we added minus 1 plus 1, or plus 1 minus 1. Underscore n was 1. Here underscore n is 2. Underscore n is 3. Minus 1 is 2. Plus minus 50 is 50, and so on. And so these are the numbers for this series that we have. It actually ends at 191. Later on, we'll add 1 to the end of it because we forecast. I'll explain that later. Okay, let me clear this. Now let me show you what this next command does. This format date var %tq. What it does is it just, in the data set, it converts those numbers to dates for convenience. They're still numbers to Stata. It still uses them as numbers, but it just converts them so that you can read them easily. So let me show you what happens with that command. Remember, we just looked at date var, and it was minus 52 to something. Let me run this again, get past this graph. All right, here we go. So now let's look at the data again. And now see the date var variable, oops, is nice and convenient. We know what they are. So our data set runs from 1947 Q1 down to 2007 Q4. As I said, I add 1 later because we're going to do a forecast. But the data set ends at this line 244 initially. Okay, let me clear this. We'll come back to the results. So then what you say is you have to say time series set. And you just set the date var, whatever. You could call this something else. You could call it date 1 or whatever you like. Quarterly dates, whatever you want to call it would be fine. Just use the same name in these 3 places and forever else. I'm going to use it a lot here. Now, I decided for GDP I wanted to take out the Great Recession because for a single series forecasting, having the Great Recession, we probably need a model to handle that, to do it right, and I didn't want to have to deal with all of that. So I'm going to end the data in 2007 Q4. So I just said keep if the date var is less than, and it needs a number. It can't read, I can't just write 2007 Q4. So I say 2TQ 2007 Q4. And remember what that does. That's number 191 in the data set. So it's telling it to throw out all observations whose identity number is greater than 191, greater than or equal to, or greater than. So I'm going to keep everything less, 191 or less, or 2007 Q4 and less. I'm also going to start everything at 1982 because there's some structural breaks in the GDP series. Like the variance, for instance, this is the Q2 is really the beginning of the Great Moderation. Q1, this is good enough. The Great Moderation, the variance of output is half of what it was before that. So there seems to be a structural break in this series at 82, and I didn't want that in there. I didn't want a known structural break in there. We're going to test for unknown structural breaks later, but so I just start everything at 1982. So we'll get to this in a second. So the data set's going to be 1982 Q1 through 2007 Q4. Now this next part's not really needed, but I want to show you how to do it. because sometimes it's useful to know how to lag a variable. So the first thing it does is simply convert the real GDP data that I read in up here into logs. So I called it ln r GDP. So, and then I want to create some differences. So the first thing I create is the first difference in real GDP, which is just the log of real GDP minus the log of real GDP in the previous period. So you just put bracket underscore n. Remember, that's that system variable that keeps track of which observation it is from 1 to t minus 1. So this just says, if I wanted to, I could have put this in there to make it really clear exactly what it's doing. That's just the default. I could have said that log of real GDP at n minus the log of real GDP at n minus 1. But underscore n is the default, so we don't have to put that in there. And then I'm going to need the lags. I'm going to need up to 6 lags of the change in real GDP, the change in the log of real GDP. So then I just lag these by including these n minus 1 or n minus 2 as needed. So this is the way you would lag a variable. There's actually a built-in function that does this automatically. That's why you don't need this. But sometimes it's useful to know how to do this. So I thought I'd just explain it. You don't really need it, as we'll see. All right, the very first thing you're supposed to do in your program, up to this point, really the only thing you're going to have to do is change the variable names. You're going to have a different end of sample. Yours is going to be 2012 instead of 2007, so you need to make that change. And your data set's going to start at a different place, so you're going to need to make that change too. But other than the variable names and the dates, you're all set to go. So the first thing you're asked to do is a Dickey-Fuller test. And I said to do it with 3 lags. I actually did both 3 and 4 in my example program because I wanted to look at both. I was tempted to do 2 as well, but probably should have. But I only did 3 and 4. So what this says is do a Dickey-Fuller, augmented Dickey-Fuller test on the log of real GDP. So I want to find out if I need to difference the log of real GDP. And here I'm going to set my sample. So if the date's greater than or equal to the number associated with 1982 Q1, or it's less than or equal to 2007 Q4. So this is just setting the sample. And we'll be using those a lot. Your sample's different. So just be aware of that. And I'm not going to keep saying that, but throughout the program, your sample's going to be different, so you're going to need to change it appropriately. Shouldn't be too hard. And then this is the number of lags in the augmented Dickey-Fuller test. Remember, this is, you regress it, you regress this variable on its lag. Actually, you regress the change. You regress the change. To do the Dickey-Fuller test, you regress the change in this variable on the level of this lagged, and then a bunch of lag changes. And this tells how many lag changes should be in the model. Just look this up in the text. Can't remember what page it's on. Let me grab it real quick here. Gonna have a little dead spot for a second. Sorry about that. Should look this up before I got started. Dickey-Fuller 556 it appears. So just look on page 556. No, it's not there. I must have read it wrong. Anyway, it's in your text. You can look at it. Oh, here it is. 558 is where it is. And the test is explained on page 557. So you'll be able to take a look at that if you've forgotten how the Dickey-Fuller test is done. And it's also on the video. It's explained in detail on page 559 if you've forgotten about that. Okay, so to do the Dickey-Fuller test, that's all there is to it. You just do this command right here, and you're all set. So that shouldn't be too hard. So let's run it and see what happens and take a look at that. let me clear this. Let me clear these two. I should comment that graph out so we don't have to wait for it every time. I'm going to do that. That's this. The graph is this TS line. I'll come to that later. So let's see what happened with the Dickey-Fuller test. Let's go up here to the top. So here it is. This is the very first one. So the test statistic, so the augmented Dickey-Fuller test, this is the number of lags here. It gives you the number of observations and so on, is right here. That's the test statistic. And the p-value for 5%, you can see that you would fail to reject. And what you're failing to reject is a unit root. And so in this case, it looks like we do have a unit root. We do have a non-stationarity problem. And so we're going to need to fix that. And the answer didn't change when I had 4 lags instead of 3. In fact, it's pretty much the same. So adding that extra lag, looks like that extra lag doesn't do anything. Okay, so now we know we need to difference the data. So we will. So see this command d dot. That command will difference the data automatically. Let me, oh, I don't have my reader open. Let me show you something that might be useful. One second here. I need to get to the 421. Oops, wrong thing. There we go. I posted this on your assignment. If you go to section 14, where is it? Let me search. Oh, that's not what I want. Let me try that. Not something else. I need to get to section. Here we go. So if you go to section 11.4.4 of this manual, it will explain what I'm about to talk about. But if you put, so they're using GNP. This is really old. It should be GDP. But if you put L dot in front of it, say the variable's x, you'll get xt minus 1. L2 dot, so L2 dot, I don't know what this LL is. L3 dot GDP would be the third lag. Oh, I see. That's the same as doing this. So L3 dot GDP will give you xt minus 3 and so on. This will difference. D dot gives you the difference, and that's what I'm using in the program right now. And so I posted this manual. There's all sorts of things in here you can read about if you want. But this is in the time series section down here, which is what we're doing right now. So if you want to read about the Dickey-Fuller test, it would be here. Oops, how come it didn't come up? This is old. Anyway, it's all there. Okay, so this D dot says, take the difference. Up here we tested the level, the log. Now we're going to look at the difference, same time period. And I'm going to use 2 lags. When I do the AIC and BIC down here, I'll find out that 2 lags is correct. And so I'm going to go ahead and just use, I already knew that. So I'm going to use 2 lags. Actually, the AIC and BIC, they're not going to give me a clear answer. They will for you. You'll know exactly how many lags you should use. But for this part, I actually told you in the homework, just use 2 lags. Okay, so let's run this and see what happens with this part. Oops, what did I do wrong? Oh, I've got, when I had something highlighted, that's all it runs. It's going, what? Okay, so this is the second Dickey-Fuller test. Here's the ones that we did before for 3 and 4 on the level. Here's the one on the difference. And now we'll see that this test statistic exceeds even the 1% critical value. So that's telling us we're rejecting that 1 minus the coefficient, 1 minus beta is 0. Or before we accept it, the test is you test that 1 minus beta is 0. And if that beta is 0, you have a unit root. Here we're finding that that beta is not 0, so the coefficient is less than 1 in the autoregressive series. If it's an AR1, if it's AR2, the sum of the coefficients is less than 1 is what it turns out to be. But anyway, this tells us that we reject a unit root. We reject the non-stationarity. And so differencing inflation or differencing GDP seems to do it for us. And so now we know that the difference in GDP appears to be stationary, and we can work with that. And so now let's go back here to the program. The next thing I ask is for the first 4 autocorrelations. In your case, it'll be for the change in inflation. So your variable will be the change in inflation. Oh, one thing I want to mention is in Stata, caps matter for variable names. So ln rGDP, that is a different name than ln GDP. So just be careful about uppercase, lowercase. If you name your variable infl like I did, and sometimes call it infl, as I did in writing checking the homework solution for you, you'll get an error. And so just be aware of that. Anyway, we want the first 4 autocorrelations. This command CoreGrm stands for CoreGrm. It actually, a CoreGrm is a graph of the autocorrelations. Remember, the autocorrelation is the correlation of GDP at t with t minus 1, t minus 2, t minus 3, and t minus 4. Those would be the first 4. So it's how correlated it is with the first lag, the second lag, the third lag, the fourth lag. And we should think that as it gets further and further away for a stationary series, that those correlations die out. So let's look, and we explained those autocorrelations in the lecture. Let's look at those. Oh, yay, no graph, because I put the comment in. Okay, where is it? Here they are. So here's the command. I tell it 4 lags. This is where I tell it how many autocorrelations to compute. That was in the command file here. And then it gives us this AC, or the autocorrelations. These are called partial autocorrelations. We didn't talk about those. Don't worry about them. But these are the autocorrelations. You see, the first 2 are pretty high, and then they die off pretty fast. If we kept going, they'd get very close to 0. Let me try 8. See if that's true. Yeah, they get pretty small. Go a little negative, but they don't get anywhere near those. And so it looks like a couple of lags, 2 lags is probably going to be enough. So that's one way to get a sense of how many lags you should have. But the other way to do it is the way we talked about, which is to do the AIC and the BIC. And so that's the next thing after the autocorrelations. The next thing the program asks you to do is to find the AIC and the BIC. Now, Stata actually has an automated code for that, estat IC. That gives you the AIC and the BIC, but it uses a different formula based upon the likelihood function, and it gives different values from the AIC and the BIC we want to use. And so what I had to do, a lot of packages have this in there automatically. This one just doesn't, and so I had to write it myself. And so this command here will calculate the AIC for this regression. So the first thing I do is I run a regression. So I want you to do this for lags 0, for p equals 0 to 8. So for no lags, so there's no lags in this model. In this model, there's the first lag of the difference of log of real GDP. So I run the log of real GDP, or the difference, sorry. Here's the difference on the first lag. The next one, I run the difference on 2 lags. And I only went up to 6. This last one runs 6. You have to go all the way to 8. But it's really easy. Once you have the first one written, you can just copy it. And plus, you'll have this as an example program to edit. But once you have the first one, you can just copy it, paste it, and then just add a variable, copy, paste, add a new variable. It doesn't take long. So what the heck does this thing do? Okay. These regressions put out some automatic variables. So help, Stata command, reg. If you go down here to the bottom, it gives you a list of stored results. So one is en, which is the number of observations. And then the other one I'm going to use is this eRank. And that's not very informative to you, but it's the rank of EV. I'll talk about that in a second. So, and there, like ERSS is the residual sum of squares. I also need that. It gives some degrees of freedom. You get R squared, adjusted R squared, the root mean square error, all sorts of things. For panels, you can get the number of clusters. So those are nice. Then there's some macros you can do, like get predictions. We're not going to talk about these, but when you're more advanced, you can use those as well. Okay, so what this does is it takes the results from this regression and it calculates the AIC and the BICs. The first thing, inside quotes here are just comments. So I just, on the output, it says AIC for P equals. And P is equal to this eRank variable minus 1. What eRank is the number of coefficients. It's technically the size of what's called the variance covariance matrix, but the size of that thing, and that thing's square, the size of that thing, or its rank, is equal to the number of estimated coefficients. And so this eRank, in this case, would be 1, because I only have a constant. Down here, I have a constant and a lag, so there's 2 coefficients. So eRank would be 2. I need, but P is what, P doesn't include the constant, so I take eRank minus 1. There's 1 lag here. That's what this is, P is. It's 1 less than the number of coefficients. And so this is just saying, telling you what P is on the output so you know what it is. And then I just threw in a colon for the heck of it in quotes, so it's a comment. And then this is the formula. So it's the log. If you remember, it's the log. You can look this up in your book. I don't remember what page it's on, but go ahead and look at it. But it's the log of RSS, the residual sum of squares, over n. So en gives me the number of observations, plus p, that's eRank, times 2 over n. If you open up to the right page in your book for the AIC, you'll see that. And then the other formula for the BIC is the log of the RSS over n, which is this part here, plus p, or excuse me, p plus 1. This term here is p plus 1 in the formula, sorry. Plus p plus 1, which is eRank, times the log of n over n. And so again, you can look up those formulas in the book as you look at this, and you'll see how they work. They are on pages 548 and 549. And then this just calculates the AIC and the BIC for lags for p equals 0 through p equals 6. Yours is for p equals 8, so you're going to have to add a couple more to this. One thing I did just to show you it was the same, mostly I use the automatic functions. So this is the fourth lag of the difference of the log of real GDP. But since I created these other variables up here, which are the same thing, in the last two I went ahead and used them just for fun. But this could have just as easily been L3.lnRGDP here. I just use the other format. It doesn't make any difference. This is more convenient because you don't have to define them up here. Okay, and this will put out a series of AIC and BICs, and then your job is to pick out the one that tells you which is the correct number of lags. And so on the output, what you'll see is here's the autocorrelations. You can see there's a little spike down here, but usually those are just randomness. It's really these first two that are important. That's telling me that an AR2 is probably a good idea. And then here's the AIC for p equals 0. It's minus 10.20. Now I got some strange numbers here that the AIC and the BIC did not give me a clear picture of what the best model should be for lags. So I relied upon the autocorrelations rather than the AIC and the BIC. For your homework problem, that doesn't happen. So don't worry about that. They're going to be consistent. But I decided that an AR2 was the best given what I was seeing. So let's move on here. The next thing that you need to do is to forecast one period ahead. I'm going to forecast 2008 Q1 because my data ends in 2007 Q4. You're going to forecast 2017 Q1 because your data is going to end in 2016. So again, you're going to have to change the dates. What this does is it says, when we did the TS set up here, I think it went to, what was it, 192 or something like that. It went through 2000, well, since I did the keep, the end of my data set's 2007 Q4. So I don't have a date variable that goes beyond that. There's no room in the data set for anything else. Since I'm going to forecast one beyond the end of my data set, I need to add another observation. I need to add space for that forecast in the data set. That's what this does. It says time series append. Then I just tell it what the last data set is. If I wanted to forecast 4 periods ahead, I would say 2008 Q4. We're only forecasting 1 period ahead, so I only added 1 observation. And then this just tells it what the format is. It says the time series format is quarterly, TQ. If it was monthly, that'd be TM. If it was annual, it'd be TY. It just tells it when I format this extra. Seems like it ought to know by now we're using quarterly data, right? But it doesn't. So you have to tell it, and that's all that part's doing. Now here's the regression. So I'm going to do a forecast. So I first need to do a regression, and we're always adding the robust errors, just as a reminder. Here's a regression. We're using an AR2, so I'm going to regress the difference of the log of real GDP on first and second lags. And I want my data set to be from 82 through 2007. Then this set of code right here will do the forecast for you. So this is the way you do forecasts in Stata. So what you first have to do is store the results from this regression. So that's what this command's doing. It's saying, take the estimates and store them. And this is a name you get to choose. I called them AR2est. You could call them anything, but I called them AR2est. So store those estimates. That's separate from the forecasting. That's just storing the estimates. Then we're going to start the forecasting. So first need to create a model. So we just give it a model name. I called it AR2 model. You can call it anything you want. So this creates the model. And then I'm going to forecast using the estimates I've stored in AR2est. And I need to rename. This is just a technicality when I'm using these d dot variables. I probably should have been using caps here. Turns out it doesn't matter for this function, but just to be consistent, I probably should have used a cap there. Anyway, but where was I? Oh yeah, this thing, this names. This messes up the name of the variable that you're forecasting. Oh, excuse me, this part. When I use this d dot, it gets confused about what the name of the variable I'm forecasting is exactly. Because there's only there's not a variable in the data set called d dot ln rgdp. There's only a variable called log of rgdp, and that's not what we're forecasting. We're forecasting the difference. So I'm just going to give it a variable name to store the forecast. I'm going to call it d log rgdp1. I probably should have called it f, would have been nice because it stands for a forecast, but I didn't think of that when I wrote this program. And then I need to put a prefix under the forecast. So this will just say anything that's a forecast has a prefix of f underscore. And you'll see this in a second. And so this set of code is going to do the forecast for us. So we run the regression, store the estimates, create a model, associate the estimates with the model. That's what this is doing. And then give a name for the series we want to put the forecast in. Then this forecast solve is what actually creates the forecast for you. So it says, solve this problem, give me a forecast, put a prefix of f underscore on any variable that's a forecast, begin the forecast in 2008 Q1 and end the forecast in 2008 Q4. If I wanted 4 of these, I could have put 4 here. That would estimate the model through 82 Q4 and use those estimates to create forecasts from Q1 to Q4 of 2008. That would be a 1-step ahead forecast for Q1, a 2-step ahead for Q2, a 3-step ahead for Q3, and a 4-step ahead. 4-step ahead because we only estimated the model through 2007 Q4, and this is 4 steps ahead of that. But I only want to do it for 1 step ahead. That's all I'm asking you to do. And then this just lists. This is the name I gave the series to store the forecast. And then it automatically puts this prefix of f underscore in front of it. So I just want to list the forecast if the date var. In this case, I probably should have said, the way you say equals in an if statement is you have to use a double equal sign. So this just says if the date variable equals 2008 Q1, list that particular variable. So let's run that and take a look at that forecast. So I got to get through all the AIC tests we did. There's 4 lags, 5 lags, 6 lags. And then here's the regression that we ran. We store these estimates, create the model forecast. Starting is 28Q1, ending is 8Q1, 2008 Q1, forecasting 1 variable over 1 period. And this is that list statement I did. List is what you do to display series. Display is for scalars pretty much. List is for series. So here's the forecast for 2008 Q1. I can tell you that's not a great forecast because that's when we started going into the recession, and we're forecasting GDP to go up by about 0.6%. If you multiply these by 100, which I didn't do, you'll get the percentages. actually, these were quarterly data. If you multiply by 400, so this is a quarterly forecast. I should make that clear. This is a quarterly forecast. You have to multiply by 4 to get the annualized forecast. So it's about 2.4, 2.5%. And then you can multiply it by 400 to get the percentage. So if you multiply this 0.06, this number by 400, you would get the annualized growth rate. And let's see, 4.8, carry, no carry. Yeah, it's about 0.0, but it's about 2.48, 2.49, something like that. Just quickly doing it in my head. So not a good forecast because we're going to do a recession, but there it is. Okay, we're almost to the end. Now the next part is the most complicated part of the assignment. In the assignment, you are asked to do a series, to do pseudo forecasts. So this is the pseudo forecast section we're at. And that's pretty much the end. And you have to do those pseudo forecasts over a bunch of different time periods. I'm going to do mine from 2005 Q1 through 2007 Q4. So 3 years, so 12 different forecasts. And these are all one step ahead forecasts. And I couldn't find a command, it may be in there, but I couldn't find it in Stata to automatically do a series of one step ahead forecasts. So I wrote a program that would do it inside of a do loop. I could have done something similar up here, nested this in a do loop, and then just changed the variable entries each time, but that's actually kind of a complicated do loop to do because you have to add a new entry each time. And so I didn't do that one, but this one wasn't too bad. Now I could have just written 12 different regressions and done 12 different forecasts. To do that, you would do it just like this. So the first one would be this, except we're going to do pseudo forecasts. So these are within sample forecasts. We're going to artificially in the data at a certain point, and then I'm going to artificially in the data at 2004, and then forecast 2005 Q1, and then artificially in the data at 2005 Q1, forecast Q2, and so on. Those are called pseudo forecasts. You can read about them in the book. We talk about them in the video, I believe. But anyway, instead of doing this for each, if you can't figure this out when you get to this part, you can do a series of individual regressions. So in this case, I want to estimate it from 82 through 2000. And this first one here, I'll estimate through 2004, Q4. And then I want to forecast 2005 Q1. So this would do the very first thing that's going to happen when I do this do loop. This 4 values, date 1, sets up a do loop, as we'll see. Then I could copy this, Control C, and run it again. Got a lawnmower going by. Hope you're not picking that up. Hope it doesn't last too long. And then I could run the second regression. In that case, I want to run it through 2005 Q1, and then run then do the forecast through Q2. And then this would list it. And then I could do this 12 times to get all the forecasts from 2005 Q1 through 2007 Q4. But I didn't want to have to run 12 different regressions, though in retrospect it's probably not that hard. So let me undo all of this. Okay, back where we started. And so I did it in a do loop. And so you can do it either way. Just do this part 12 different times and just get one step ahead forecast, or use this do loop. So what this does, these are some variables I'm going to want to use later on. So I first set sum1. I was going to use sum for the variable name, but sum's a function, and I didn't want to risk having this be a function. All of the functions in the program usually don't have numbers on them, like sum1 like that, or for1. So just to be sure, I kind of routinely add these things to my variable names. The ones don't really mean anything other than, just in case it's a function, I put the 1 here so it doesn't get mixed up. So I'll explain what these do in just a moment. So this sets up the index. It says, for the values date 1, I could have used date, but I was worried that was a function, so I added a 1 to it, equals, this is a different way of getting those numbers I talked about, these variable numbers, the date numbers, sorry, that Stata uses. It's just instead of TQ, it's a YQ. There's a YM and a YY and a YW for monthly and annual and weekly and so on. But this, you just tell it the year and the quarter. Here's the year and the quarter. And this thing here is on the left-hand side of your keyboard, and this is the normal apostrophe. But what this does, this just gives me the number. I haven't tried this yet. I wonder if this will work in a display command. It might not. Yeah, it'll just give me the number. I could have said display TQ, same thing, 2004 Q4, and it should give me the same result. Yeah, 179. You see that? So that's just a way of getting those numbers. So this is 179, and this number, well, what the heck is it? Let's find out. 2007 Q3. Let's just quickly change this to 7 and this to a 3. And what do we get? 190. So what this says is for date equals 179 slash means 2, 190. So it's going to run everything between the brackets. The first time it goes through, it'll set the date 1 equal to 179. Second time through, it'll be 180. Third time through, 181. Fourth time through, 182, and so on, all up to 190. So there's 4 values. There's a couple of other 4. You can do this for strings, too, if you want to change variable names. It's for each. There's another function called for each. But 4 values is what we're using because it's numbers. These turn out to be integers, doesn't matter. So this just says, for date 1 running from 179 to 190, run this set of code. So the first time it goes through, it says, okay, run the second order regression and use the sample from 1982 through date 1. And date 1 is 179. It's 2004, quarter 4. And then do the forecast. Now remember up here where I set the, we had to use a different name, this names thing. I need a different name every time this loops. So what I did is I called it d log r GDP, and if I put this thing with no spaces here, it'll append whatever number that is to this thing. So this just creates a different variable name each time through. The first time through, it'll be d log real GDP 179. So it'll look like the variable name the first time through will be DLN RGDP 179. And then it'll be the same thing the second time through, but it'll be 180. And so on until the last one will be D log RGDP 190, and so on. So that's all that's doing. So run this up until this date. The first time the date will be 2004 Q4, then it'll be 5 Q1, 5 Q2, 5 Q3 each time it loops through. And there's no header, no table. If I don't have that there, it's going to print the whole regressions every time, and the output gets huge. So I just suppressed the regression output with these commands. And then the R at the end here just is the robust standard errors. When you're debugging, when you're first writing the program, you should go ahead and have that there because you can see what's going on in the regressions, and sometimes that gives you a clue to finding errors in your program. But after you get it fixed, get all that stuff out of there so it doesn't clutter up your output. Then I just repeat what I did up here. We store the output in this AR2est each time through. It'll store a different value. Create a model. If I try to create a model that's already been used, as this one has, it doesn't like it, so I have to tell it to replace the one that's there. I could have done this trick. I could have created a different model each time through by just putting this here, then I wouldn't have to replace. But I didn't need all those different models, so I just went ahead and replaced it. Okay, and then so this is the variable name, and then we're going to forecast, and I want to begin at the date plus 1. I want to forecast 1 period ahead. If I wanted to forecast 2 periods ahead, 2 steps ahead, I'd make this plus 2. And I only want to go to 1 period ahead. If I wanted 4 steps ahead like we did above, based upon just that sample, I could make this a 4. And it would give me the begin of plus 1 and the end of plus 4. That would give me 4 different forecasts. But I only want 1. And then this is another way. This just suppresses some output on the over here on the output screen. You wouldn't have this in the first time through, but that just gets rid of the. And then here I just list the output. Now, we're forecasting 1 period ahead, but the date value is date 1, but we're forecasting into date 1 plus 1. I want to print that out. So what I'm going to do is if the date var is equal to date 1, I'm going to list 1 period ahead, f dot of the forecast. The whole variable name is, here's the variable name here. Remember, we created a variable name here, and it appends that f underscore to the forecast. So f underscore, whatever this is inside the parentheses, is the forecast. F dot says, I need it 1 period ahead because we're forecasting 1 period ahead. I'm listing for date 1, but the forecast is in 1 period ahead, so I'll just take the future value and do the same thing for a real GDP. Now, you're asked to compute the root mean square error, so that's what this next part does. I haven't actually saved this yet. Let me put in a comment here. Begin calculation of the root mean square error, and I better not forget the semicolon. As you have probably done already, you know that'll give you an error. Okay, so I created this variable up here called sum1. It goes from 1 to t. It's got the full length, t plus 1 actually, because I added another with it. TS append, we added 1 extra observation to the data set. So it runs to t plus 1. I created this variable called sum1. The first time through it says set sum1 equal to the first value of it is 0. That's what it is in the when this is 179, when it's 2004 Q4, that 179 we calculated over here. Sum1 will be 0 plus, and here I just calculate the difference between the actual value and the forecasted value squared. I'm doing this at date 1, but remember we've stored these 1 period ahead because we're forecasting 1 period ahead. So I took the future values to grab the right values. I put the F dot in front of it. So the first time through, this says take sum 1 equal to 0 plus this deviation squared. The second time through, when date 1 is equal to 180, and these are stored in 181, it says sum 1 equals whatever it was last time plus, so this is the squared deviation, this thing for when the date was 179, and this is the squared deviation when it was 80. So it adds the new squared deviation to it. The next time through, it'll take I've got those, the 179 and the 180 square deviations summed here. It'll add the third one to it. So this is adding up the sum of the squared deviations. We need that to calculate the root mean square error. So there'll be 12 of them because I'm forecasting from 2005 Q1 through 2007 Q4. So in the end, this will add up all 12 deviations. And then here I just want to store the forecast somewhere. So I just stored the, at date 1, I store that future value of 4.1. I'm going to have to, well, I'll come back to that later. So this runs through 12 times or whatever that you'll run through a different number of times because you're going to forecast for a different number of periods. Your forecasting period, I believe, is 2008 Q1 through 2012 Q4. So that'll be 20. Yeah, that's 5 full years. So that'll be 20 different times it'll loop through. If you did them one at a time, like I was explaining, you'd have to have 20 different regressions. Then this is just finishing off the calculation of the root mean square error. So it's the square root of that sum over the number of observations. This is the way you count the number of observations. This is TQ at 2007 Q4. That's 191. This one is at 5. That's 180. So this is 191 minus 180, which is 11. Then to get the number of observations right, you need to add 1 to it. If I have observations 7 through 9, 9 minus 7 is only 2, but I have 3 observations, 7, 8, and 9. So you take 9 minus 7 plus 1 to get the number of observations. That's what this is doing. It's taking 191 minus 180, 11 plus 1 is 12. We had 12 observations, remember? Yours will be 21, if I counted right. So this just finishes off the root mean square. It takes this sum, takes the square root of the sum of squares over n, the number of sums that we added up. And I do this for Q3 because that's where I stored it. The very last iteration here is Q3, 2007 Q3, when we forecast 2007 Q4. And so I store it there. Then the root mean square error, this is stored in the wrong place. It's really for the 2004 Q4. So this just says, set the root mean square error to the lag of what I did here. This just puts it in the right place. Let me show you something. So let me list RMSE1 and RMSE if date var, what do I want to list them for? Let's just, I don't want to list the whole thing, greater than, equal to the number associated with, let's start at 2006. Start 2004 Q4. Let me run this. Oops. What did I do wrong? Huh. For some reason, that command didn't work. I did something wrong. Oh, equal. No, that's... What did I do wrong? Oh, remember I said caps in lowercase matter? I used a cap. Okay, let me clear this. Should know better. Good lesson. So let me go up here to where I listed them. That should be at the end. So here's where I listed these variables. Right at the end, I only calculate them for one variable. So here's RMSE1. This 243 is actually, this is yet another set of numbers. Those are those underscore n's. This 243 is 2007 Q3, and that's where I stored the root mean square error, 1. All this command here does, where I take the, let me get rid of this. I don't need that anymore. That's this list. All this command right here does is set root mean square error here to the lag of this. So it just puts that in the right place. It says this one is this lagged. And then I'm just going to list it. And so, oh, the other thing that happened, sorry. So then I just list the root mean square error. Now, you don't need to do this because I didn't ask for the graph, but the forecasts are actually stored wrong too. I stored the forecast. This is F dot. This is the forecast for date 1 plus 1. I stored it in date 1, so I need to fix that. So I just do that with it by lagging it again. I called that 4.1, so I could call this 4. And then that's just so I could graph it. So when we're all done here, we can actually use this TS line statement if you want to take a look at your forecast. And this is a good way to debug. If these things are just, sometimes you'll get a flat line down here, weird things going on, you'll know there's a mistake in your program. But here's what our forecasts look like. Wasn't doing too bad up until the period of the recession, and then suddenly we're forecasting it goes up when actually it starts going down. But you can graph those forecasts that way. The very last thing to do, we're almost done, is to test for breaks. And for that, you can use a can routine. Let me get rid of this and get that out of the way here for a second. In the text, it talks about a QLR test for a single unknown break in the series. I actually want to save that code. Just a second. I want to test for a single unknown breakpoint. And what that is something called a soup-walled test. In the book, they call it a QLR test. So there's something called a soup-walled statistic. If I use this function called estat SB single, that means a single break, a single unknown break. So single break, and it's unknown, and estat is what does it. There's some other statistics called AWALD and ALR and others. You don't need those. You could actually leave that out. I put them in there just because I wanted to see all the tests. And this tells it, you can read about it in the book, but if you're too close to the endpoints, this test doesn't work for breaks. So you want to throw out a certain percentage of the observations at the beginning and the end. This says throw out 15%. That's the default. I didn't have to put that in there, but I did, so you can see how to change that if you want. In the instructions for this, you can actually trim differently on either side. So that there's an L trim and an R trim. There's actually even more statistics in the A-walled, E-walled, and S-walled. We want this supreme walled test. That's the QLR statistic. That's actually the default. There's some other tests like an ELR and so on. Don't worry about those. You don't need them. You only really need this S-walled. And if you wanted to know what this puts out, like if you needed for some reason to work with a chi-square statistic, R in parentheses, R chi-square, chi2 would give you the chi-square statistic like we looked at for the reg command. But anyway, this just runs the break test. So let's do it, and then we're going to be almost done. So here's the forecasts in this program. I actually didn't run it. Let me go up here a bit. So here was the end of the AIC. We looked at that. Here was that single 1 period ahead forecast. Here's where we begin the loops. The first period we forecast is 2005 Q1. Here's the forecast, the F underscore. Here's the actual, so you can look at them. And then it calculates the difference squared, as we talked about for the root mean square error. So this is for Q2 and so on, and it does all 12 of them up until the end, which would be 2007 Q4. Then we generate those root mean square error statistics, and so our overall root mean square error is about 1.1%, which isn't great. So our forecasts are off. That's like one standard deviation. So plus or minus 2% is not great in terms of forecasts. Okay, and then here's the QLR test. What we want, this isn't actually the QLR, it's a little bit different, but it's close enough that you can use this one. To do the actual QLR, I'd have to do another do loop and loop over a bunch of F statistics, choose the maximum F statistic. This test is just as good. Interestingly, for the S-walled test, if you look at the p-value, we reject that there's no break. So it looks like there's a break, but the other two statistics don't give a break. So then you would kind of wonder and experiment around a little bit and make sure you really have a break. But purely by the S-walled statistic, if we just play it by the book and said, that's the statistic we chose before we started, that's the one we're going to obey, which is the way you ought to be doing this. We have a break point in the data to worry about. And we'd have to now try to figure out where the break is and then figure out what to do about it. But we're not going to go through that exercise. So that should do it. That should give you the things you know to do your homework problem. And so I hope it goes well. I'll see you next time.